Oh, it's so good to see you all today. Here I have a tuning fork. Can you hear it? I hope you can. I can hear it. But how can I hear it? How is this thing even making a sound? Well, if the camera were not laggy, and if you could see in full definition, what you would see right now is you would see that my tuning fork is vibrating back and forth and back and forth and back and forth. Well, it turns out this is how all sounds are made. All sounds come from vibrations. Today, we're talking about sound waves. Now, when we talk about sound waves today, the biggest thing that you need to know about sound waves is that all sound waves are longitudinal waves. All sound waves are longitudinal waves, and here's really deep down how a sound wave happens, is that you have something like this tuning fork that vibrates back and forth. And when it vibrates this way, it squishes on some air. The little molecules, air molecules right here next to it get squished. When they get squished, those little air molecules then push on the little air molecules next to them and squish them. Then those little air molecules push on the air molecules next to them and squish them. Then those little air molecules push on the air molecules next to them and squish them. And you get a little chain of a little compression that compresses the next little bit of air, that compresses the next little bit of air, that compresses the next little bit of air. And that sound wave, that compression gradually travels through the air. Meanwhile, back at the tuning fork, it just went this way in its vibration, but then it vibrates back the other way. When it pulls back the other way, when it went this way, it compressed the air. When it goes back this way, it creates a little rarefaction, a little region of low pressure air. Then you have alternating regions of compressions every time it moves this way, rarefaction every time it moves this way, compression every time it moves this way, rarefaction every time it moves back this way. And the compressions travel through the air from the tuning fork or from whatever the source of the sound is, all the way to your ear. When these little compressions make their way through the air to your ear has little hairs in it, and those little hairs are standing up. When they get hit by a compression, they get flapped on down, and when they get hit by another compression, they get squished on down. And your brain takes the little squishes of your little hairs in your little ears, and it says, hey, that's sound. Is that not incredible? If you're not impressed by your brain right now, like seriously, I don't know what is required to impress you. That's insane. Your brain interprets all of these little air compressions that press down on all of the little hairs inside of your ear and says, yeah, that sounds like something. Is that not wonderful? Now, there's a little bit about sound. I always ask students, after we talk about how sound is a longitudinal wave and how all sound is created by vibrations, I always ask students, does sound need a medium to travel through? And the answer is yes. All sound requires a medium. All sound waves require a medium to travel through. All sound waves require a medium to travel through. If there was no medium for a sound wave to travel through, well, that sound wave would have nothing to squish. And if it has nothing to squish, if there's nothing to compress, well, then there's no way that little compression, there's no way that little sound wave can travel through anything. In outer space, there is no sound. Everything is silent because there's nothing anywhere. In a vacuum, there's nothing to carry the sound. If you had an explosion in outer space, it would be absolutely silent. Because the explosion would happen, that would for sure create some vibrations, but because there's no air to compress, you'd hear nothing. Sounds can travel through a variety of mediums. We most of the time hear sound waves traveling through air because we live most of our lives in the air, but whales also can hear lots of sounds, and they live in the water. Turns out that sound waves can travel through solids. Sound waves can travel through liquids. And sound waves can travel through gases. Sound waves can travel through all three. As a matter of fact, it actually turns out that sound waves travel the best in solids and the worst in gases. with them traveling mediumly well in liquids. And here's why, is because in a solid, all those little molecules, all those little particles are tightly packed together. So when a vibration hits one of those little molecules, well, it's already right next door to its next door neighbor molecules, and it goes ahead and squishes those, which go ahead and squish the next one, which go ahead and squish the next one. This is very different from air, where the molecules are all spread out. And if you get a compression over here, it's a while before that compression runs into another molecule all the way over here. Happens eventually, but takes way more time. So because the density of a solid is so much greater than the density of a gas, it makes solids much better at transferring sound waves. You know this because if you take a spoon and you hit a piece of steel, you can hear that cling from the spoon hitting the steel crazy far away, way farther actually than your voice could travel through the air. Take the Golden Gate Bridge, for example. Take a visit there, a little field trip action, and take out your little spoon. Hit the Golden Gate Bridge with your spoon. Someone on the other end of the Golden Gate Bridge will be able to hear the sound of your spoon hitting the metal. You know what they won't be able to hear? You yelling on the other side of the bridge. Sound travels way better in solids, but there are some caveats to that. Sound doesn't always travel the best through all solids. In fact, in order for sound to travel through a medium, that medium has to have some amount of springiness to it. It has to have some amount of bounce backness to it. It has to be able to go boop, 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 a little bit of elasticity, a little bit of springiness. There are some solids and some materials that just don't have the same kind of springiness or the same kind of elasticity. Take like the sound panels that are on the sides of the movie theater, for example, or the ones that are set up all over an audio recording studio. If you've ever been in an audio recording studio before, you'll see that the walls are all lined with this kind of black, foamy, squishy sort of stuff. The walls are lined with that sort of stuff because it's a sound absorber. It keeps sound from bouncing off the walls. And the way that it does that is it's just made of a squishy material. That's all. If you've ever jumped into a foam pit before, like at the trampoline park, then you really will understand how these things work. You know, if you jump down into a foam pit, that foam pit just allows you to sink down into it. It doesn't, spring you back up like a trampoline does. You sink down into the foam pit and you just stay there. Same thing happens when a sound wave runs into one of these sound panels. The compression is on its way in. It hits one of those sound panels, and when it hits one of those sound panels, it just squishes in, just like you would in a little foam pit. Those foam panels, the sound panels, they don't have a lot of elasticity or a lot of springiness to them. So when the sound wave hits the sound panel, it just kind of absorbs it. It doesn't push it back out again. And so because those things don't have much springiness, they aren't very good at transferring sound or transmitting sound waves. Sound waves don't travel through them very easily because in order for a sound wave to travel through, you need something that can compress and then stretch back out again, and then compress and then stretch back out again. Those sound panels don't do that very well. They're not very good at compressing and springing back into action. So sound panels are used to absorb sound. In general, solids are the best at transmitting sound, but you gotta have something that has a little bit of springiness or a little bit of elasticity to it. Now that's a little bit about the mediums that sounds travel through. Next we're going to talk about properties. Let's go back to the pen. Next we're going to talk about properties of sound waves. Now, when we talk about properties of sound waves today, we are going to specifically talk about two properties of sound waves. The first property of sound waves that we're going to talk about is frequency. The frequency of a sound wave corresponds to how high-pitched or low-pitched the sound wave is. A high-frequency sound is a high-pitched sound, and a low-frequency sound is a low-pitched sound. Remember, frequency is just number of waves per second. So if you have something that makes lots of compressions per second, something that vibrates back and forth very, 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 very fast, that's something that's a high-pitched sound. High-pitched sounds are made by fast vibrating things. Low-pitched sounds are made by very slow vibrating things that oscillate back and forth and create compressions very slowly so that you only get few compressions reaching you in a certain amount of time. So the frequency of a sound wave corresponds to its pitch. Now, most people can hear frequencies between 20 hertz and 20,000 hertz. Between 20 hertz and 20,000 hertz. Anything below 20 hertz is called infrasonic. Anything above 20,000 hertz is called ultrasonic. Frequencies below 20 hertz are called infrasonic, with infra meaning below and sonic meaning sound. Things above 20,000 hertz are called ultrasonic, with ultra meaning above and sonic meaning sound. So there's your word within a word STEM moment for the day. We can't hear infrasonic sounds, and we also can't hear ultrasonic sounds. An infrasonic sound, if you went below 20 hertz, like if you asked a speaker to give you something that was like, let's say like 2 hertz, that's 2 oscillations per second or 2 waves per second. If you asked a speaker to give you 2 hertz, it would give you something like that. Bum, 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 bum. 2 little clicks per second, 2 vibrations per second. Now, that you would hear initially as individual sounds. You would hear it as individual clicks. But if you turned up the frequency, if you made it go faster, it would start to go. It would get faster and faster and faster. As it got faster and faster and faster, those clicks together would start to blur, and your ear would start to hear it as one sound, a very, very low tone. Right around 20 hertz is when you would start to hear that really, really low tone. As you know, as people age, they actually lose hearing and they lose frequencies of sound. So as you get older, you lose these higher frequencies and you can't hear the ultrasonic sounds as well. That is a gradual process that happens with aging, but it's not really what people are concerned about when they're concerned about you losing your hearing, because those super, super high-pitched sounds at 20,000 hertz, we don't really use those very often in our daily lives. What people are concerned about when they are afraid that you're going to lose or damage your hearing is they're concerned about you losing the second property of sound waves, which is the intensity. Of a sound wave. The intensity of a sound wave corresponds to the volume of a sound. And the volume of a sound, or the intensity of a sound, depends on 2 factors. First, it depends on the amplitude. The amplitude of the sound wave. And second, it depends on your distance from the source. The amplitude of a sound wave is determined by how much air gets compressed, or how much of the medium gets compressed in a longitudinal wave. In a longitudinal wave, the number of compressions per second, that determines the frequency, but how big the compression is, how much air gets compressed, that determines the amplitude. This is why explosions are so loud, is because they compress so much air so fast. They have a really huge compression where a lot of air gets compressed. The more air that you compress, the bigger the amplitude. That is what you change when you change the volume dial in your car. When you turn up the volume in your car, you're changing the amplitude of those speakers. In other words, you're changing how much those speakers push on the air. You're making them push on the air more when you turn up the volume and push on the air less when you turn down the volume. So the amplitude matters. The other thing that matters is the distance away from the source. You know this. If you stand super close to a speaker while it's making a sound, you hear it really, really loud. But if you stand really far away from a speaker while it's making a sound, you hear it nice and quiet. The reason for this is because all sound waves expand outwards in these giant spherical circles, kind of like how ripples in a pond expand outwards in circles. Sound waves are like 3D ripples in the air that's around you. And so when you have a sound wave, it expands outward in this giant 3D sphere. Now, as you get further and further and further away from the source, the sphere is getting bigger and bigger and bigger. And so the sound wave is getting, you can think about it as the compression is getting less and less concentrated. And if it's getting less and less concentrated, it sounds quieter and quieter and quieter as you move further and further away. So the intensity depends on two things. It depends on, first, the amplitude of the sound wave, and second, on your distance away from the source. Now, we can write this, actually there's an equation for intensity. The equation for the intensity of a sound is equal to I equals pressure not pressure. This P stands for power. It's power divided by area. Power here, the power of a sound wave, you know that power relates to energy, and you also know that the amplitude of a wave relates to energy. So this one you can think of as the power is related to the amplitude of the wave. The area here, that's the surface area of that giant sphere of the sound wave. So this area right here shows you your distance away from the source. As your distance away from the source increases, the radius of that giant sphere increases, and as the radius increases, this area increases, and as the area increases, your intensity decreases and the volume decreases. You don't really need to know this formula specifically, but you do need to understand it conceptually. So again, we're not going to do any math with it, but you should understand conceptually that this part corresponds to energy, which corresponds to the amplitude, and this part, the area, corresponds to the distance away from the source. When we talk about units of volume or units of intensity, the SI units are watts per meter squared, because you got the units of power divided by the units of area, meter squared. However, those aren't the units that you most commonly see. The units that you most commonly see are decibels, named after Alexander Graham Bell. It's a decibel. Decibels, the only thing that you really need to know about decibels today is that you just need to know that decibels are based off of a ratio of intensities in comparison to the threshold intensity for human hearing. So these aren't, like, decibels aren't an actual measure of intensity. They're a measure of a ratio of intensities. If that ratio is a really big ratio, like if it's like the threshold of human hearing is this much intensity, that's like the lowest amount of sound that you can hear, or the smallest volume of sound that you can hear, and you get a volume that's like this big, that's going to create a bigger ratio versus if you have a volume that's like this big, and then the threshold for what we can hear is this big. So decibels are comparative. It's very relative. It's relative to what the human ear is capable of hearing. So it's very much about humans. Decibels are very much about what we are capable of hearing. These units, watts per meter squared, are the more general units that apply to any sound regardless of how we perceive that sound. So that's a little bit on the two properties of sound waves. The last thing that we're going to talk about today before we go is the speed of sound. The speed of sound is, as you know from Sonic the Hedgehog, very fast, but it's not the fastest thing out there. The fastest thing out there, you probably know, is the speed of light. Light is the fastest thing out there. As we'll see, I'll write this down in a second, but as we'll see, the speed of sound in air is about 330 meters per second. That's about 750 miles per hour. Let that blow your mind for a second. That is a crazy, crazy fast speed. But while the speed of sound is about 330 meters per second, the speed of light is 3 times 10 to the 8th meters per second. That's 3 with 8 zeros after it, meters per second. That's a crazy, crazy number. So the speed of sound is fast, but light is way faster. You used this discrepancy between the speed of light and the speed of sound when you were a kid. And your parents taught you to use this discrepancy to calculate how far away a storm was from you. You know that when you have lightning and thunder actually happen at the exact same time. You know when you get off the trampoline and you shock your friend? You get a little shock between your fingers? Hey, that little shock, isn't that just a mini lightning? It's a little transfer of electrons from one place to another. That's all that the little shock is. And what's crazy is you can hear it too. When you shock each other, that little shock, you can see the little flash of light and you can hear the little tiny pop. Well, that's just mini thunder. Here's what happens when you have lightning, is that you have some electricity that moves down, you have some electrons that move down. It's a big old shock, and that big old shock comes with a big old pop. And that big old pop is what we call thunder. Now here's the deal. If you have a storm far away in the distance, the light will take some time to reach you from the lightning, but it'll get there pretty quick. Even though the light and the sound from the lightning both start at the same time, the light is moving way fast, so it'll get to your eye very, very quickly. The sound, though, is lagging behind, and it'll take time to get to you. You learned when you were a kid that you could count the number of seconds between when you saw lightning and when you heard thunder. You count the number of seconds when you see the lightning, that's when it first gets to your eye, and then you count until you hear the thunder. When you hear the thunder, you take that number of seconds that you counted between the lightning, which got to you first, and the thunder, which got to you second, divide it by 5, and that's the number of miles away that the storm is. Very, very nifty trick to know if it's time to stop playing outside and to start coming back inside, based on how far away the storm is. So we can use this discrepancy between the speed of light and the speed of sound to measure distances. It turns out that the speed of sound has an equation. Here's an equation for the speed of sound in dry air. The speed of sound in dry air is equal to 331 meters per second plus 0.6 times the temperature that day in degrees Celsius. This is the equation for the speed of sound in dry air. And I don't like my box, so I'm going to fix it. Doop, 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 ba-ding. Okay, there it is, the speed of sound in dry air. Now, as you can see, just looking at this equation, the speed of sound really depends on a number of variables. Well, the first variable that it depends on is the medium. Do you see how this equation really only works for the speed of sound in air? This is not the speed of sound in steel. It's not the speed of sound in water. It's the speed of sound in air. In fact, the speed of sound in steel is about 15 times faster than the speed of sound in air. So really significantly changes depending on the medium. The next thing that matters here is temperature. As you can see in this equation, if you increase the temperature, you're actually changing this number in this equation. You're adding extra to it. That's because as you increase the temperature, you increase the speed of those little air molecules. If you increase the speed, you increase the kinetic energy of those little air molecules. They run into each other more often. And if they run into each other more often, it's easier for them to transfer sound, transfer that compression from one place to the next. So temperature matters. The next thing that matters, as you can probably see from my subscript here, this is the speed of sound in dry air, is humidity. Humidity matters for the speed of sound because as you increase humidity, you're adding water molecules to the air. When you add those water molecules to the air, those little H2Os, those little water molecules are very, very small and much more mobile than the clunkier O2 and N2 molecules. And so because they're a little bit more mobile, they can transfer sound just a little bit easier than they can. So the speed of sound goes up on a humid day. The next thing that matters is almost so intuitive that sometimes students don't even think about this one, and the next one that matters is wind. You actually for sure know this because you've experienced this in your life, that on a really windy day, sometimes it's way harder to hear someone. Well, that's because wind can either work for you or it can work against you. If I'm trying to talk to somebody who's sitting over there, oh wait, let's make our camera big so you can see it. If I'm trying to talk to somebody who's sitting over there, and I send sound waves this way, and the wind is blowing back this way. Well, that sound wave is kind of like walking on a moving walkway at DIA, except if you're walking this way and the moving walkway is moving back this way, it'll slow you down. Even though the sound wave's trying to move this way, the wind is moving back this way, the air is moving back this way, and so it moves forward much slower than it would if the air was perfectly still. However, if you had a day that was very windy, but this time the wind was blowing this way and you were trying to talk this way, well, that would be very helpful to you and make the sound travel faster. Like when you're walking on the moving walkway at DIA as that moving walkway is moving forward. So sound moves forward this way and the wind moves forward this way. It helps to carry the sound there faster. So wind is one of the last things that really matters for the speed of sound in air. And these right here are the most significant factors that determine or that impact the speed of sound in air. And that, ladies and gentlemen, is just about all that you need to know about sound waves for today. I hope that you learned something fun and that it made your life just a little bit more wonderful. Have a great rest of your day, and I hope to see you soon. Bye, good people.